Okay, so now we're gonna see what are block ciphers. First of all, block ciphers belongs to the category of transposition ciphers, and the steps involved in implementing block ciphers are as follows. The first thing that you do is you select some integer m. Select an integer m and split the message in blocks of m sizes. Okay, so if we have the message, let's say stop corona virus, so we need to and our m is selection of m is equals to 4. So we'll split this message into blocks of 4. But then we arrive at a problem that what if our message is not a multiple of 4? So then always there will be some blocks which won't have all 4 letters. So how are we going to come over that problem is by inserting dummy letters of our own. So let's say we add a dummy letter A here. Okay. And next what we do is we come up with a function, and we call that function the function phi. So we say so phi of 1. So for the phi function is defined by ourselves, so it does not have a particular you say mathematical representation, but it just says that phi of 1 is 3, phi of 2 is 1, 4, 2. So it must be a function, and it must be a bijection function, so that its inverse is also possible. So I hope you all remember what bijection functions were. We had injection, surjective, and bijection. So bijection functions were the only class of functions for which we had an inverse of functions. So we need bijection function so that we could have decryption function as well. So in block cipher, we need to have a function that should be a bijection function. And what it does is it just maps the position of each letter in a block to some other random location. So we'll see this in practice. So what we need to do is assign these numbers 1, 2, 3, 4 to each of our block. So we'll say, okay, this is 1, this is 2, this is 3, and this is 4. This is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And the letter that's in the first position will move on to the third position. That's in the second position will be mapped as going to the first position in the block. The letter that's in the third position will be mapped onto the fourth position in the block, and so on and so forth. And now what we do is So this is the first letter in the block, and it should be mapped onto the third position. So we move it to the third position. This is the second letter in the block, and the function says that it should be moved to the first position, and that's what we're gonna do. And this is the third letter in the block. The function here says that it should be moved to the fourth position in the block, and that's what we're gonna do. Then we have our fourth letter in the block, and it should be moved to the second position in the block, and that's what we're gonna do. And then our function will come on to be t, and that will be p, s, and o. Okay, so you can see how we are just repositioning each letter in the block to some other letter in the block. So we're just shuffling them up by some technique that we call the function phi of n. So this is our shuffle function. So the next topic we're gonna see is called crypto systems. So it is a formal way of assigning, consolidating a crypto system. For example, Caesar cipher systems or block ciphers. So it's a formal way of compiling all the forms of Caesar ciphers into a single system. So a crypto system consists of a five tuple, okay? And the tuples in this, I will elaborate them in detail, are P, C, K, E, and D. So P stands for the plain text, and C stands for the cipher text or encrypted text. So for example, in our Caesar systems, we cannot directly work on alphabets. So we need to work on integers, and those integers range from 0 to 25. And the ciphertext is, since we are always taking a mod of 26 and it remains in the same space. So these both belongs to, in a example of Caesar system, these both belongs to Z25. And from our previous lectures, you can recall that Z25 were the numbers ranging from 0 to 25. Again, this will be the same. It will be Z25. So then we have our key space. In our Caesar cipher, we could only shift to the right. So that's why we are restricted to only the positive numbers. And after 25, if a key is 25, it does not make sense to have a key that is 26, because that will be equal to having a key of 0. So the message will repeat itself. So again, for Caesar cipher, our key space will be between 0 and 25, and that will be the integer space Z25. So what will be the E stands for encryption function. And for our Caesar cipher, our encryption function is nothing more than just subtracting the plain text, adding with our key, and that will be the key K, and taking the mod with 26. So the encryption function, set of all encryption functions. So actually, E is set of all encryption functions. So there can be more than one encryption functions, and here our encryption functions varies with the key. So it depends on the key. So whatever the key we are taking, the encryption function is P plus K, and that makes gives us a set of encryption functions. And similarly, the D stands for set of all decryption functions, and in our scenario, our decryption function is dk, which will be equal to p minus k, and again taking the mod 26. So that's our crypto systems, uh, formal definition of a crypto system. But the main point here is, which have been highlighted here, that's necessary for a crypto system to work, is whenever you apply a decryption key or decryption function to the plain text, and then you again apply decryption function to it, the answer you must get is the plain text again itself. Okay, so I am going to highlight this because this is the, so what this says is that whenever you apply a decryption function to the encryption function, it is the job of the decryption function to return us the back again to the plain text. So keep this in mind. Okay, this is the decryption function. So we're gonna take a 15 minutes break, and then we're gonna come back